talk is to give it without being either hated or killed at the end. And hopefully we'll get there. So what I want to tell you about is, actually my goal in this talk is to tell you about the open question. And I want to start with a paper, fast-forwarding Hamiltonians, exponentially precise energy measurements, with my student, Dorit. And I encourage you to go read the paper, because I'm not going to talk about really the details of the paper. I'm just going to tell you the minimal things that we need to know in order to explain the open problem. And the open problem has to do with things of interest to this conference. Basically, is it possible to somehow prove that there are no shortcuts in generating the thermal field double slit? So,
generating time evolution.
Yeah, and functionality. So, okay, so we're going to start very far. Time, energy, and principle. So, we have an input, Hamiltonian, H, and we have a state. I'm given a state psi, which is an eigenstate with energy E, and I want to measure E with high accuracy. And in order to do that, I apply a measurement by applying some H measurement, which is not the same as H. And the time, energy, and enthalpy principle says that delta E, the error in estimating E, times the duration I apply H measurement, is at least a constant. Okay, great. So some facts about this. Most cases seem to satisfy it. We already know from 69 by Aharonov that there are cases in which you can actually validate arbitrarily large relations by just increasing the norm of H measurement. Just this divides the time by the same factor. So can we characterize when the time energy asymmetry principle is or is not valid and to what extent? So the first main step is forget about this time energy asymmetry principle, replace it by a different version, and in the spirit of this conference, replace time by complexity. So the version of the time energy asymmetry principle is now a computational version, where time is replaced by the computational complexity of performing the measurement. And this is kind of weird at first, but if you think about it, this is really what we're interested in, because before it was really not very well defined what are the H measurements that we are allowed to implement. And you can actually do various Feuerstichen, what is that word in English? I don't know. Games and stuff like that, like in our own form, where you increase the norm without paying anything. If you do want to really account for all the physical resources that you are paying to perform the measurement, this is what you need to do. You want to count the computational complexity of applying the measurement. By that I mean the number of gates to apply the measurement. Okay, so that would be the time energy asymmetry principle that I want to be interested in. Now, I'm sorry?
Something dimensionally peculiar. I'm thinking that delta E, delta T is greater than...
Yeah, so there's a hidden time here in the sense that how much time you take to implement the gate, for example.
Yeah, okay, fine.
Okay. So that would be my time energy asymmetry principle, and I encourage you to talk to me during lunch to argue if that's a good principle to talk about. But let's take that principle and think of it as an interesting principle and try to see what we can gain from it. Okay, so I think that now that we have complexity in our hands, we can actually go and study things much more rigorously, or we can try to characterize this, which systems do or do not violate much more rigorously. And what we get is an interesting theorem, which says that in fact, those systems that allow violations of the time energy asymmetry principle, meaning delta E is exponentially small and the computation complexity is still polynomial, those systems are exactly those systems which allow what I call fast forwarding. meaning those systems which allow simulation of e to the I minus IHT for time which is exponential, in complexity which is just polynomial. So this should remind you of shortcuts. Okay? So those classes of systems are the same. And basically the proof idea is, the essence of the proof is very simple. If you think of fast forwarding and you want to derive highly complex energy measurements, what you would do is, suppose you have fast forwarding, you would start with your eigenstate and a controlled qubit, and you apply a controlled h to the time t, and you get this extra qubit with this phase, and t, because of fast forwarding, can be exponentially large. And if you generate many qubits like that with various t's, polynomially many t's in between 1 and 2 to the n, you actually can, with classical processing, measure this in the Hadamard basis, classically process it, you get E with exponentially good accuracy. And the other direction is not very complicated. It's actually technical to make things work here, but I'll spare you the details. So we do get this equivalence between two classes which seems not very related, those that violate time energy assembly principle exponentially, and those that allow fast forwarding. Okay, so what can we understand from that about those classes? So there are various examples of classes which we can fast forward. Commuting local Hamiltonians, quadratic Hamiltonians, Hamiltonians that come from Shor's algorithm. It's an open question of whether many body optimization Hamiltonians can or cannot be fast forwarded. Okay, but now comes the question. Is it possible that every Hamiltonian can be fast forwarded? And the answer comes in theorem 2. No. There is no generic fast forwarding procedure that takes any physically realizable Hamiltonian and makes it fast forward it. And this theorem assumes that PQP is not equal to P space, which is a commonly believed assumption. Okay, so because I want to, next slide, I want to state the open problem, I want to actually spend 2 minutes on the proof. So how does the proof work? Okay, so if I want to show that there's no generic fast forwarding procedure unless PQP is in P space, what I actually could, the way I could actually show that is I could take a P space complete problem, meaning a very hard problem. You don't have to know what P space is. And if I find a way to actually solve it on a quantum computer in polynomial time using fast forwarding, that would be sort of a big no-no. Okay, so how do I do that? Here's a very hard problem, P-space complete problem. It's called other end of the line problem. So you're given a graph by means of a circuit, which computes the graph, and it's a graph on nodes made of n-bit strings. And the circuit gives you the outgoing edge of the node and the incoming edge of it. And actually, there's just one of those in most. So the graph consists of cycles, path, and isolated nodes. And the question, you're also given a node which is at the beginning of some path. And the question is, find the other end of the line of this path which starts with this node here. Okay, so find this node. The only thing is that this path is exponentially long. So how would you find it? Naturally, it looks like, well, define some Hamiltonian from this graph and fast forward it along here. But actually, this intuition doesn't work so well. What you can do is you do something very simple. You do build a Hamiltonian based on this graph. So zeros everywhere except for ones for each edge, connecting a node and another node. And then, well, we know that we can, if you can fast forward, you can actually measure this with respect to eigenstates of this Hamiltonian with very high accuracy, exponentially good accuracy. And if you check this Hamiltonian type by the model, well, the eigenvalue spacing is not too bad. It's not worse than 1 over exponential. So So you can actually perform a very accurate energy measurement, meaning project on one eigenstate, approximately. So here is the algorithm. You start with a node, V. You project on one eigenstate, and the eigenstates are well spread on the path. And then you measure again in the computational basis a node, and with good probability you have progressed a little bit along the path, a fraction of the path, and then you start all over again, except you adjust your Hamiltonian so that you can't go backwards. So regardless of whether you understood the details, the point is that that you could use this Hamiltonian and fast forwarding of this Hamiltonian, which means highly accurate energy measurements of this Hamiltonian, to solve a p-space complete problem. So that means that you cannot fast forward this kind of Hamiltonian.
Because you don't believe that.
Because we don't believe that
Each
that's,
space is in PQP.
yeah, exactly. So this is a computational assumption that is very strongly believed to be true. That you can solve such a problem in quantum phenomena. Okay, so good. So under this assumption, theorem 2 implies that there is no fast forwarding for this H. Okay, so now the open question. How do we prove that there's no fast forwarding for a given Hamiltonian like the CFT Hamiltonian? How do we do that? And an observation here is that, in fact, suppose we can show that a given H is universal, is computationally universal. I'll talk a little bit more about the definition in a second, but suppose we can do that. Then this H would be able to simulate this H corresponding to the graph efficiently. And then, if we could fast forward H, we could also fast forward this H of the graph and solve a p-space complete problem. Big no-no. So that means that we cannot fast forward the universal H. So if you show that H is universal, it cannot be fast forwarded. Okay, so suffice to prove that if you want to show no fast forwarding, it suffices to prove that a Hamiltonian is universal. If you can show that HCFT is universal, great. A step towards this is to show that a typical Hamiltonian is universal. Now, I would like to make a remark about the notion of universality. Like, people are talking about universality, essentially meaning almost everything. So there are various ways to when you hear universal, it can mean various things. So first, universal set of gates, that means you can generate any unitary from those gates. Universal family of Hamiltonians, for example, the Hubbard model is universal because if you want to simulate some system by a quantum simulation, you can tweak the parameters of this Hubbard model explicitly to simulate that. That's universal Hamiltonian, family of Hamiltonians. I'm talking about a different notion of universality. I'm talking about a notion in which the Hamiltonian is, a particular Hamiltonian is computationally universal. So fix a Hamiltonian, and the universality, the fact that it can compute any computation, is manifested by the fact that you can encode the computation in the input and then let it evolve. Okay? So it's a fixed Hamiltonian. If you're familiar with Conway's game of life that Charlie mentioned before, that's exactly the same idea. It's computation universal. You have a fixed set of rules, and by changing and encoding and sort of preparing the input correctly, efficiently, you can perform universal computation.
But with a fixed Hamiltonian, you could only visit things, unitary operators on a torus. On a torus, just because of energy.
You have to give it an infinite Hilbert space somehow to make it universal, right?
But I think what Dorit wants is the complexity theoretic kind of universality, right? And specifically what you want is that when you run the thing for exponential time, that it will do p-space, in a polynomial space, right? So, it's almost
Right.
a tautological
So actually, in
definition.
order-
And that doesn't mean that you visit every state, or every.
Well, you have to visit an exponential number of states.
Yeah.
That doesn't mean you
No,
have to
no,
visit
no,
every
look at
state.
get approximately close to any state.
I mean, that would,
Look, sorry, you can only get states on a torus.
like,
I'd like it
Like
close
if
to a
you-
state with a greatly different energy.
right.
Yeah, that's Okay.
Right, well.
But you can start from any state you want.
So maybe
Right,
it's
if you were-
including universality.
Right, if you were restricted to a computational
Right.
subspace, but within that there were exponentially many states,
Right.
that would
Yeah,
still be
yeah.
fine.
Yeah,
for
right,
you.
you're right.
Yeah.
So it's but it's universal in the sense
Yeah.
that, yeah, so that's exactly the distinction between a universal set of gates and computational universality. You don't want to generate any unitary.
So isn't it good enough that the energy levels be commensurate?
I don't think so. No, for example, just the diagonal momentum. Okay, so and I want to mention that this is actually not known even classically. We don't know that a typical cellular automaton, in some sense that we can talk about later, a random cellular automaton is universal, even classically. But on the other hand, this is not a hopeless problem. Unlike most, we heard about P versus NP and P space versus PQP, which you shouldn't try. This is a problem that is probably very difficult, but solvable. So just to wrap up with the connection to Lenny and Scott's result, so basically Lenny and Scott have also a no-go fast-forwarding theorem, a no-go shortcut theorem. And they say that there exists a unitary such that the term of the Douglas state written up there cannot be generated efficiently unless some other computational assumption. And the connection between the two is that they talked about generating states, and I talked about simulating Hamiltonians. My task is easier when I want to show that it's impossible. Okay?
In other words, harder.
In other words, harder. But in any case, but also for their task, if you can show the same question, is a typical H computational universal, that would actually imply their result for typical Hamiltonian. And this question actually has implication not only for this question of shortcuts, but also if you go back to the time energy asymmetry principle, if you can show that a typical H is universal, you would also show that a typical physical system satisfies the time energy asymmetry principle, which we currently don't really understand why or how to characterize this. So this would be an explanation here. Okay.